Alright, so this is going to be 5.1b, reciprocal quotient and Pythagorean identities. So we've talked about the identities. We've talked about cosecant being the reciprocal of sine. Secant is the reciprocal of cosine. Tangent is sine over cosine. Cotangent is cosine over sine. All of this is on your formula chart. Something that hopefully you've kind of gotten used to by now is when you multiply reciprocals, because they are indeed reciprocals, they multiply to 1. Multiply to 1, multiply to 1. So there we go. Alright, now example 1. We've seen this just a few times, but example 1 is the exact example of difference of squares. It is really important that you recognize these things quickly, because the quicker you are at recognizing them, the better off you're going to be. So this is the difference of squares because they are the exact same thing. 1 cosine A, 1 cosine A. The difference is separated with a plus, separated with a minus. The basic examples of difference of squares in algebra are x plus 3, x minus 3 multiplies to x squared minus 9. You don't have to do the algebra involved in that. So think to yourself really quickly, what is x plus 5 times x minus 5? Or what is x plus 10, x minus 10? So you get to the point where you don't think about it anymore. You just know that it's going to be x squared minus 5 squared. So x squared minus 25. And x squared minus 100. So same thing for trig. It's going to be 1 squared is 1 minus cosine squared. There's not really a good reason why they're using the letter A instead of x. It's silly. No good reason. And then if you look at your Pythagorean theorem, this is an exact Pythagorean theorem. Look at your handwritten Pythagorean identities, and you'll see that that does match up to sine squared. And again, they're using the letter A instead. So that's where we were supposed to go. Alright, transform secant x over sine x minus sine x over cosine x. So I'll start by rewriting the problem. Now, some people would do this in different ways. It really doesn't matter how you do this. So for instance, a lot of people would just say, well, I have fraction minus fraction. I need a common denominator. And if that's what you want to do for your first step, that's great. Other people would say, well, let's put this secant, because everything else is written in sines and cosines. Let's put this secant as a sine, or not a sine, a cosine in the denominator. And if you did that, honestly, that would kind of save you a step, but it also costs you a step. So it's really the same thing either way. My personal opinion is as soon as I see fraction, plus or minus fraction, I do common denominators. So that's the way that I'm going to do it. If you want to come in and see me, I'll show you that other way. So what I'm going to do though is I see the denominator of sine here, so I know that this fraction needs a denominator of sine, which it currently doesn't have. So I'll multiply to get that sine in the denominator, but we do have to accommodate by doing it on top as well. Over here for this fraction, I see a cosine over here, so I need that, and so I'll do a cosine on this side. Alright, so what ends up happening is that when you multiply this times this, you end up with a cosine that multiplies times a secant. Now, I'm not going to write this out anymore. Reciprocals multiply to 1. If you were in my class right now, I would be banging on the table. You do not need to be spending more than one step to do this. Cosine times secant is 1. And then I have cosine times sine. That doesn't really multiply to anything, so I'm just going to have to write that out. Cosine times sine. Then I have my minus sign, minus operation right here. And then sine times sine is sine squared. And cosine times sine, cosine x times sine x. Alright, so the reason why we got a common denominator was to add across the top, or subtract in this case. So that makes 1 minus sine squared all over cosine times sine. All right, and now at this point, I can say, so if this is the point that you get stuck, then honestly, you went a really, really far way, and you should be really proud of yourself. It's just a matter of recognizing Pythagorean theorem. When you get stuck, go to your formula chart, see if you can recognize something. And so it should be this thing right here that you recognize. So look at your formula chart, see if you can find this. So the reason why I know to do this is because when you have a 1 with a trig squared, it doesn't matter which trig it is, it's probably going to match to one of those Pythagorean identities. So which one does it match to? So you should be looking, you're looking, you're looking. You see that it matches to cosine squared. And so I still have cosine sine. All right, and now at this point we basically are done, because if you have cosine squared on top, what that's really like is cosine times cosine. So I can officially say this crosses off with this, or equivalently what I've started doing is just crossing off the 2. So you're left with cosine x over sine x, which is cotangent x. Which, if I go back, hopefully that's where I'm supposed to end. And it is. So, cotangent x. Alright, number 3. This is an algebra problem. I call it algebra because you have something on the outside that multiplies like distribution 1. So let me rewrite the problem. And now this is that distribution step. I know it's distribution because I have something on the outside with these parentheses. So when I distribute, I end up with sine multiplying times cosecant. So you know what that multiplies to. Yes, 1. Now I have sine once again, and it multiplies now times negative sine, which makes negative sine squared, which is Pythagorean theorem, cosine squared. All right, number 4. This is a new problem for us. Now, I am not saying that this is the only way to do it. This is a way that will be very beneficial to you later on. Okay? So, what I notice is that within this problem, I have some group plus some group. Let me rewrite the problem because I can't work with that tiny script. Okay, so once again, I have this group plus this group. And what I notice is that within both of those groups, they both contain cosine squared. So we have this algebra step that takes it out of both groups. Can you think of what that's called? So that's called greatest common factor. They both have that common factor of cosine squared. Let me come over to the side and just kind of show you what I'm doing back to algebra, and then we'll go back. I don't know if you don't like this. I don't really care. I'm going to do it anyways, but this is like saying 2a plus 3a is the same thing as a 2 plus 3. Okay? And you could go on from there, but when they both have the a, you like pull them out, and you get that. All right, so now with trig, they both contain that cosine squared. So I'm going to take out that, cosine squared. And what you have to do is you have to imagine multiplying it back into. So what I mean, cosine squared times what here gets you cosine squared. Well, it's already there, but you still have to multiply something. You have to imagine distribution. What would you multiply it times to still get cosine squared? So 1. 1 is what you multiply it by to get itself. Now, cosine squared times what here gets you plus tangent squared cosine squared. Well, I've already got the cosine squared, so that would be like multiplying it times 1 again. But you still have to count for the tangent squared, so I'm going to need to fill in a tangent squared here. The best thing I can advise is now in your mind actually do that distribution and make sure that you could go backwards a step. With these proofs, you should always have the ability to go back a step because you didn't do anything illegal mathematically. All right. So from here, what I notice is that 1 plus tangent squared. I don't know which Pythagorean it is, but I absolutely am hoping that this is a Pythagorean theorem, because if it is, it's going to make things a lot easier. I don't know how, but it will. So look at your Pythagorean theorem, find where this 1 plus tangent squared is. What do you get? Alright, so you should have gotten secant squared for this thing right here. So that inside the parentheses is secant squared. I did not touch the cosine squared. It is still there. What happens when reciprocals multiply? That's right, they multiply to 1, which is where we were trying to go. All right, now, if while I was talking you tried to do this and you did it a different way, that's fine. Let me show you the other way. No, I don't want to show you because people that did it with me, this is the good way to do it. So if you did not do it this way, you should go back and redo it. If you want to try to figure out the other way, you can. Just know that this is that greatest common factor is going to become really important. All right, number 5, we've actually done. The top becomes tangent squared and sine x. Pythagorean theorem was that first step. So now I can say, well, I see the fact that I have a tangent and I want a tangent, so I'll leave one of those tangents. And then I have another tangent, and then I have a 1 over a sine. So all I've done is kind of expanded this, right? Because if I have tangent squared, that's tangent times tangent, and then if I have a sine on bottom, that's 1 over sine. So now I say, well, let's look at what I got. I got a tangent. I want a tangent, but I don't have this secant. So secant is 1 over cosine. So let's see some more sines and cosines. So what I'll do in my next step is instead of writing this tangent, I'm going to write sine over cosine because that's what tangent is. So I'm rewriting that first tangent because I like him. He's desirable. But this tangent I'm writing as sine over cosine, and this I'm going to keep as 1 over sine. So now what happens is this sine with this sine go away, and I'm left with tangent times 1 over cosine, which is secant. And still tangent, so tangent times secant. So we're done.